So first of all, is pretty raw presentation in a sense that I don't have any discussion from the theoretical point of view or chemistry point of view. I will show you the script that Amir talked about. So, and also Amir already covered what we need to calculate the coupling, all the prepared required file, how we will get. So my presentation is pretty just talking about showing you the script. Maybe all of you have that script, but little bit modified here or there, so you can match what you need to change in future for your purpose. So what do you need to calculate the coupling? You need mainly the 4 different files. It's already discussed. One is the Wavecar old and Wavecar new. The Wavecar old and Wavecar new, from the name you can guess it. Actually, it should be T and this one should be +1. So, oh, my bad. This one is correct, yeah. So when you calculate the different step in adiabatic trajectory, so your current step is considered as a T. So you will get a Wavecar from that bus calculations. And then you can copy that Wavecar as a Wavecar new. So these two actually basically same Wavecar file. And then you will get the Wavecar old from the previous calculations. So similarly, after doing this calculation in one step, when you're going forward to the next step, you will rename this Wavecar new to the Wavecar old, and then you will get a Wavecar new in the following step. So you need to continue these iterations in every time steps. So if you consider the time step at T, that means we will have a one Wavecar new and we will have a Wavecar old from the previous calculations. And you already seen what is the energy pop and input overlap file. The input overlap file is contain the informations about how many which molecular orbital you're going to calculate. Like here, okay. So for example, we looking on the orbital number from 118 to 117. If you notice that difference is the 100, so that means we can assume that 167, that's the home orbital, 168 is a LUM orbital. So 50 up and 50 down, total 100 orbitals. And this one is the protein, is from the 0.5. So most of the script what they have from the Svetlana and Dimitri's group, I assume that they work only on integer protein. So this didn't work for my style. I change it to the fractional. So in your case, it will be 1 or in integer number like 1, 2, 2, or 5.
Javad, can you say in which cases you need protein smaller than 1 or bigger than 1?
So when we have a calculated model of the very light element like carbon or organic molecules, most of the time their frequency, phonon frequency is very high energy. Smaller frequency, in that case, we need to get the smaller protein, otherwise we will miss that every wave function number. I mean, what's it called, the wave number. So this protein usually is supposed to be the smaller than wave number. And when you're doing a calculations of a model, you can get and assume or guess of this protein from the IR frequency. Usually it should be less than IR frequency or comparable with IR frequency. For heavy metals, like semiconducting metals, if you use the quantum dots, you can use the larger, like 1 or 2 most of the time. So it's depending on your model. So in this case, this example I'm showing you from the graphene, there has a carbon, oxygen, hydrogen, they are very light elements. So I think this would be better to calculate the using the smaller proteins. So another file, next file you need, Amit already shown you the file that's input energy underscore pop. So that file is contain the atomic orbital energy and their occupation number. This one should be the starting and end number of this molecular orbital from 118 to 117. It's total 100 lines. So that script is written in such a way that is read only the number of line which we requested. So you should be start from 118, or if you're very interested, you can modify the script. Then in that case, you can read any number, but today is not irrelevant in this case. So in this one is the HOMO and this one is the LUMO. My LUMO is partially occupied because of bandgap is almost closed, it's graphene system. But in your calculation, you will expect that these two occupation numbers should be 2 and this one should be 0. And let's go to my presentation here. So then if you have these 4 files, and then you can run the script name is a similar name, overlap with something. There are different versions, different modifier name, you will get it. So if you have interest to look on the script, what the script actually does, very briefly, I'm showing you what it does. First, it will read the input file, input overlap file. It will read all states. And the second section, it will read the energy underscore pop. So in future, if you're interested to change something, you need to look on this section and this section if you is related to this energy underscore pop. So it doesn't do anything, it just read the number from the file, your input file. And then the next section of the script is look on the file. Amit already show you the file name, the build data and coupling and OS strength. So build data is a coupling. It's contained all coupling between the different conformations. I'm coming up with that. What is the different coupling is written, and this coupling is a total coupling, considering the 2 time steps. And OS strength is oscillator strength, what you use for to simulate the absorption spectrum. So these 3 are file types. You will get output from this script. Okay, so now how it's read the Wavecar file. Actually, I presented as a presentation mode. So as I mentioned, it will read the Wavecar old. It will follow and store that information in a matrix name. And it will do the similar things for Wavecar new. There are nothing, it's just a repetition of same things. And add this information in a different array. And then it will do some calculation, is read the coefficients, how it will do this coefficient reads from the both Wavecar file. You don't need to go through everything here. I'm just looking on this.
Can you just very briefly comment what are those coefficients since you touched it?
Okay, so this is a coefficient in the first is to calculate each orbital is a linear combination of multiple number of plane wave. That plane wave coefficient you're getting from the Wavecar file, and that coefficient is defined actually molecular orbitals.
Okay, so it's expansion coefficient for expanding quantum orbitals in the basis of plane waves.
Yeah.
Okay.
So in other words, linear coefficients of the linear combinations coefficients. So it is stored in this matrix here. And so then this is I guess your mic is mute now.
What is IC and I? Is it correct that IC is index of in the line 258? IC is the index of the orbital and I is index of the plane wave?
So IC is the number of plane wave coefficient in the and I is the number of orbital. And if you look at NPW is the total number of orbitals in a Wavecar file. So this, I didn't go through that one. Actually, these informations need to read on the header of the Wavecar file. So they have a way to read on that. And also, oh, okay, sorry about that. I missed this one. Actually, NPW is not a total number of, is from the I band is the requested number of molecular orbital, total number of band, and minimum and max is the number of requested molecular orbital number. And And then is do these all calculations, is calculate from the SE and SE, their coefficient is just calculate and multiply this number and getting the dipole and all these calculations. And what do you need? We will get the final of this section. We will get oscillator resistance, and we will get a overlap from these equations here. So this equation, this overlap is actually, if you look at here, this SE and SE. So this means this overlap in Wavecar new and Wavecar new. So this is not from the total overlap. So this is just overlap on the one static states. So that I'm showing in the next step here. This is the important one. What is actually total overlap? What is the difference of the bill data file and coupling file? So this one is the total overlap. I wrote it in a very raw format. So this, suppose like this, a wave function of the t and wave function of the t.
Sorry, Jubet. Sorry to interrupt. Would you mind just going back the slides and just curious? I mean, I just I never just curious in the K space how to evaluate the the transition dipole moment there. So your code, can you just maybe it's too small here for me? Let me.
So it's read actually grid point. This XYZ grid point. That point from the Wavecar file, and then on the center of the grid points multiplied by the coefficients, as we did on the, it's known as centroid kind of things. Yeah.
Okay.
It's centroid of the grid points, and then multiplied by the coefficients of the each grid points, and then integrate got the space.
The x, y, y, z, z, just electronic coordinate, right? X, y, z, and it's in terms of the k. K is a point, is a key point.
K is a grid number, yeah, I think. Yeah.
Grid number, okay. Okay.
So x, y, y, and z, z are the projections of the momentum in x, y, and z direction. And
yes,
in fact, we are computing matrix element of momentum operator, but there is a theorem because of the, if one neglects potential energy in compared to kinetic, then commutation of the position operator with Hamiltonian is equal to the momentum operator, and through the theorem, which we can discuss on the other meeting.
Oh, I see your point. Yeah, you're right. So I saw this opposite. So the coordinate is the commutator between P and H, or maybe the negative sign.
But you are speaking the correct way. Commutation of P and X will give of P of X and H will give P, and we compute expectation value of P.
Okay, so here is x, y, y, and z. Actually, they represent the P, the momentum.
Yes, the momentum.
The momentum. Okay. I'm sure the equivalent. This is for this needs a little bit harder to convert between the real space and the K space. Okay, I see. Got it.
Yeah. Thank you for the question.
Thank you, Jubet. Thank you, Dimitri. Yep.
Thank you, Dimitri, for clarifying that one. Yeah. So this one is a time-dependent coupling calculations method. So actually, this is the approximation here. If we get the coupling between the T and T plus minus the J of the final and the T plus 1, and then divide by 2 dt, it will give us the time-dependent coupling from the T and T dt. So if we want to calculate, we need to coupling of this term and coupling this term. We have a T. T is the porting. In my case, is suppose like 0.5 picoseconds. So we will get this total number here. So this is the actually this is script do for is repeat these two terms is kind of from here. The nx is the total number of band. In my case, in my example, is 100. So is get the overlap of T and T plus 1 and J of T and J plus 1, T plus 1 of I. So, and then subtract these two numbers, we will get a total overlap coupling. And this overlap is...
Would you please briefly comment what is AC and DC? It's not alternating current and direct current, right?
Oh, sorry, yeah, it's not. It's just a name of the one is got from the old Wavecar, and DC one from the new Wavecar. So that means that SE and DC is a T and T plus one difference. So in subsequent steps. So, and I is the band number. So if you consider state number, and J is for T, and I is a T, and J is a band number of T plus one. So that means it's repetition of 100 by 100, you will get a 100 by 100 matrix. As the Amir got a question, what is the coupling between? So it's giving us a probability. In other words, in very simple way, probability of electron transfer in a pair of orbitals. So in between, if we consider the 100 orbitals, we will get a combination of 100 times by 100 different combinations of molecular orbitals and the coupling between them. So we will get a matrix of 100 by 100. Total element is 100 times 100 in 10,000 elements. So, and then it's normalized. They have a normalization way. You just do the normalization, and finally we will get a normalized coupling this D. So that's the main things of this script lecture, and then it's just output how is written on the different file. This information is written in build data. The difference of the build data file and coupling is written only D term, and build data.g. I mean the the compressed file of build data is contain this term. This term, and whole. That means 3 different terms. So that means it's 3 times of that file. They have no other difference of that one. And although I was requested to talking about the coupling, but it's very closely related to the oscillator strength. That's why I also show you how oscillator strength is processed in this script. It's pretty simple one, because I know that in Dimitri's calculation, different methodology, you need the different format of oscillator strength file. So in your purpose, you can easily modify that one. So this one is simple one. This section in this script is sorted out the oscillator strength based on from the higher to lower oscillator strength. So if you don't want to sort it out, you can just comment out this section. And then this oscillator strength is written in the file name oscillator and coupling, OS strength, with the 3 different number, the occupied orbital, unoccupied orbital, oscillator strength, energy difference, and occupations, and other informations. If you don't want it, if you need a master optics file in future, you need to skip this part. You need to just write the number for 100 by 100 as a matrix. If you're interested, I modified that step for my purpose. I can show you very briefly here how it's done here. Otherwise, so it's like I commented this sorting out, and you need to add very small step. Oh, sorry, not here. This one. It just written all 100 by 100 metrics. So this is about oscillator strength. So this is all these things to do this script, this overlap matrix. Yeah, that's all. Okay. That's all from my side. Thank you. Yeah.
Please join me in thanking Jabed for very detailed explanation how couplings are computed. So I think it is a strong and important complement to what Amir has presented. So any questions to Jabed in addition to our discussion that we had during his presentation?
So where is this script, Jabed? Where could you find that?
So I think you already have that script. I assume that is also Dimitri has that script. It's similar. I borrow it from Dimitri. And I copy on from my home directory on the Photon. So I did not copy anywhere. I'm not sure which home directory you use, or I can share it with all of you guys here. And they have a lot of different versions based on what type of output format you want.
So Amir, let me contribute to discussion. So when you are, now I'm referring to Amir, when you are showing the scripts that execute several codes inside the BSCIPT, and it is just my keyboard was not working, it should be B script, and the letter R disappeared many years ago. So the B script executes several Fortran compiled executable like extract energy pop OS overlap .exe, and if you look into the bin directory for this OS overlap .f, F like Fortran, then it will have all this coding that Jabber was showing. So the executables have the same name as the original source code, but they have extension, either no extension or extension .exe, while the source code has the extension .f.
Yeah, I got it.
Yeah, you can look on this here. So since you will see this kind of script, there are a lot of different versions and modified versions all of it. So yeah, something start with overlap underscore norm, I assume, yeah, underscore OS.
So if anyone has intentions to modify, please do just name the modified files under different names, same as Jabez is showing here, so that original files are not changed for the future generations. But make a copy under different name or into different directory and try to modify and recompile. Sometimes it can be helpful.
Yeah, and also sometimes I experience I'm not very expert on the G-Fortran, the compiler. Sometimes compiler delete the original format and make a compiled code. So before compiling, always do a backup for in case, or if you need any change, always keep that one for your purpose. Yeah.
So more questions to Jabet? Please.
So you mentioned there was a normalization step.
Mm-hmm.
So why does it need normalization? Because I guess in like a perfect world, like you'd assume if the calculations were accurate, everything would be normalized to begin with.
So it's what's it called? It's from here. So I got that answer, but I got the exact answer now.
So, Jabet, while you are looking for this place, I'll give a brief comment and then you'll continue. So, WASP does not normalize wave functions and orbitals that are stored in the Wavecar and part charges. They do it because they choose plane waves, and instead of saving and processing normalized orbitals, they include normalization procedure. Original WASP code includes normalization procedure in the computation of matrix elements. So normalization is recomputed only inside bra and cat in the original WASP code. And since the Fortran code that Jabet is showing was based on the original source code of the WASP. So we just opened source code of the WASP, took some fragments from there and modified. And just to follow the same procedure, normalization needs to be added to everything what is computed. If if you were looking on the part charge files and trying to plot them, they go to like insane values. They are not normalized. And if one would numerically analyze Wavecar files, they also, the orbitals saved there, they're not normalized. But there is a way to normalize matrix elements of any observables in the Bryant-Cat procedure. Jabet, please continue what you wanted to say.
Yeah, that's a very elaborate answer. Yeah, I don't have anything to add there. Yeah. So I think is a coefficient is written, read from the Wavecar file. So Wavecar file is not a normalized coefficients there.
Okay, yeah, that makes sense.
So more questions to Jabet? More questions 1, more questions 2, more questions 3. If no, please join in thanking Jabet.